All right. Welcome back. Grab yourself a coffee. And we are going to talk today about electrical safety. So it's something that I've talked about a few times. And basically, there is a lot to it. This is far from covering the entire subject. But for what we do in show business, this splits really into two sort of general classifications. There's what we deal with on show site, and there's what we deal with in the shop or the repair room. So today's video, we're going to talk about mainly the repair room and leave show site for another thing. It has its own unique challenges. These principles that I'm going to talk about will apply. So when we're talking about safety, you can more or less use safety everywhere. But what we're going to talk about today is primarily in the shop and working with equipment and that sort of thing. So, without getting into a lot of details and an entire semester's worth about electricity and how it works and all that sort of stuff, the first thing to talk about is when we're talking about the safety, what are we talking about? We are talking about keeping you from passing electricity through your body, essentially. There is an equipment safety element to this, and we don't want to let the magic smoke out of our equipment, of course, but the primary thing, and whenever I'm talking on show site or wherever in the shop about this to people, the primary thing is, we want to keep people alive. And, who am I to tell you this? I'm a guy who's got a company and, I've been doing this for a very long time and I'm still alive. So that right there means that I've been doing something right. Now, I've also been somewhat educated about this, so I'm not just pulling stuff out of my butt, but I could be wrong. And definitely, communicate with the community in comments if I'm saying something that you just know is wrong, or even if you think it's wrong, let's discuss it in that. But most of what I'm going to tell you here, I'm pretty sure is generally correct. If it sounds like it's not or something, follow up. Don't just take it from me either. So the whole point of this is keeping electricity from going through your body. Now, why is this a problem? I mean, why are we concerned about safety to begin with? Well, at voltages over 100 volts, okay, so at higher voltages, while your body is not a great conductor of electricity, it can conduct it well enough. And when you come in contact with something where there is high voltage, that voltage is now passing through your body, okay? And it could go, if you grab things with two hands, it can pass from one hand through and around to the other and back to ground. Or now you can have insulated soles in work boots or whatever, or you could be standing in a puddle of water and concrete. Either way, if you grab something with live high voltage, that could also come through your body and down and out your feet into ground. Either way, it's passing through your body, and it's passing through a very important part of your body, which is your heart, which is an electrically controlled muscle. So two bad things can happen. The first being that a great deal of heat, just like when you've got maybe an overloaded circuit and you've got a power cable, or you've just got something that's running a lot of power through it and it gets hot, a great deal of heat can be generated through your body. A voltage is going through your body, and that can be not good. And I don't want to get too graphic or gruesome about it, but let me just tell you that if you've seen or heard of stories of people who make contact with high voltage, the phrase cooked is not inaccurate. So a lot of heat can be generated, and it can be really bad for your body. And of course, the other thing is this electrically controlled muscle. I am paying attention to which side. I am human, so it is over here where most of ours are. This electrically controlled muscle can be interrupted by voltage, and when that happens and it's not beating correctly and doing what it's supposed to do, then the rest of the body can have bad results. So those are the two things: heating, burning, those kind of things. And then electrically, there's even other things that can go on, not just stopping and messing with your heart, but there's other ways bad things can happen, and it's all bad. So we don't want to do that. We want to control what electricity, if any, flows through our body. Okay, so that's the main thing. Now, how does this happen? Well, it becomes a problem primarily because of one thing, and that is capacitors or capacitance. So let's take a look. I want to show you exactly what's going on here. Okay, so right here, I have in my hands an electrolytic capacitor. Now, I'm going to use words that if you're not familiar with, don't worry about it. It's not a huge deal. But electrolytic capacitor. Now, you have probably seen these around somewhere. If you've been inside of any device, they're used a lot, and they're used a lot because they are used in power supplies. And this happens to be a 25 volt, tells us right on here, 25 volt, 2200 microfarad capacitor. Okay, doesn't matter if that doesn't mean a lot to you, but what it does mean is that it has a fairly high amount of capacitance. You're not seeing things with 10 farads, although they exist, or a 1 farad capacitor. This is microfarads, which is 1 millionth, I believe, of a farad. And we look at capacitors in terms of microfarads or nanofarads, which is 1,000th of a microfarad, or picofarads, which is 1,000th of a nanofarad. Very small amounts of capacitance. Those are used in higher frequency circuits and other things when you get down into the nanofarads and things like that. But electrolytic capacitors in this size, 2200 or 4700 microfarads or something like that, are used a lot in power supplies. That's why we're getting at safety. This one is a 25 volt. Typically, the higher voltage, the larger the packages become. And if you've seen inside of some large amplifiers or things, you may see some really big capacitors. And those could be up into the single farads and large capacity and large voltage. Okay, so capacitors. Why are these things an issue to begin with? Why are we talking about capacitors, and what makes them bad, so to speak? Okay, well, as you can see, I've got this hooked up here to our Fluke meter, and I'm going to put this on DC volts. Okay, DC volts. Now, right now, you can see that there is a little bit of voltage. Okay, this is set to auto, but it is 0.078 of a volt. Very small amount, but that is voltage that is in this capacitor right now. So what I'm going to do, and I want to make sure I get this right. So I've got a 9-volt battery here, okay, and I'm going to take, I probably didn't say this before, electrolytic capacitors are also polarized. That does make a difference, a little bit less in this discussion that we're talking about here, but they are polarized, so I have to make sure that I get positive to positive and negative to negative, otherwise things won't necessarily work right. But I'm going to take this 9-volt battery, okay, touching it to this capacitor, 9.55. That's the voltage in here. So I'm touching this to the capacitor. It's also touching the leads. Now it's reading 9.55 volts, and I take it away. 9.53, 52, 51, still charged. Okay, this capacitor with nothing else attached to it has a little over 9 volts stored in it right now, because that's what a capacitor does. A capacitor is a device that stores a charge. It's used in a few different ways to do things, and one of the reasons that it's used that way is because it'll store a charge, but also one of the ways that it does that, it blocks DC. So in other words, if you've got 9 volts DC here, and I've got it going to the positive side of this, and then I've got a circuit or something on the negative side, if I just plug in this 9 volts, it's not going to get past this capacitor, okay? It's not going to leave the voltage DC. Direct current isn't available because it doesn't pass. They do pass AC current, and that is something that's exploited about their nature in power supplies and a lot of audio gear and all kinds of things. So you can see as I've been talking, we're still at 9.32 volts. Okay, I'm going to take this metal tool here, all right, and I am now going to short the positive and the negative terminals of this battery. Okay, you might have seen maybe a little flash depending on the camera. There was a little bit of a spark, and now you'll see we go down to 0.1. That's probably a measurement error there. Okay, we go down to 0. When the leads are shorted, the voltage goes down to 0 and the voltage is gone. Now, you'll notice voltage going up a little bit. That is coming from the meter, okay? The meter uses voltage in order to test things in that. So, yeah, 0.4123, you can see that it's charging up just from the meter, okay? If I go and I short it, now we're back down to 0, all right? So, capacitor stores voltage. A couple other things to talk about and to notice here while I've been doing this. Number one, I've been touching things. Nothing bad has happened to me. I'm still alive. I was shorting things with a metal tool. There was a little bit of a spark, but nothing dangerous happened to me. And why is that? For 2 reasons. One, this is a 25 volt capacitor. It is a low voltage capacitor. It's not designed for 100 volts or more. And I was charging it with a 9 volt battery, and its capacitance, its capacity is 2200 microfarads, which means it's not going to store a lot of power at that voltage. Okay, so the bottom line of all of this is this, what I'm doing here and what I have been doing, is not particularly dangerous in this configuration. However, were this capacitor or one like it encountered in another type of circuit and at a different voltage, then yes, bad things could happen. All right. So a couple of things about this demo. This is so that you can see this is what these capacitors do. This is how they operate, how they get charged. A voltage is applied, and we'll do it again just so we can see. 0.054 whatever and climbing. Put the 9 volt on. Boom, there we are, 9.55. And while it is draining by itself slowly, probably some of it through the meter, it still has charge. And then I will take this metal tool and short it. Yep, there was another little spark. You might have seen that. And now it is discharged. That's the main thing to learn here is capacitors charge and discharge. How can we then use this information to be safe? Because that's what we're talking about. Well, the first thing is we know what these things look like, and I will talk a little bit about where they find them at the end, where we find them and why and what to look for. We know what these things look like, and we know to be aware of them. So what do? Well, the first thing that we do is when we find them in a circuit, we test them for this residual voltage. Okay, so we've got something that we've opened up, and we see capacitors in the power supply circuit. That's where they would be, but we may not necessarily know that at the moment. We see capacitors, and we go, this could have a charge in it. It could have a voltage. It could be dangerous. We need to check. So we take our voltage meter and we look for power on these things before we start digging in. And if this was in place in a circuit, I would hook up a ground line to it, and then I would come in with a probe and I would go measure, and I would look and see what I've got. And if I have low, very low, or no voltage, I know that that should be safe. And if I do see that there is voltage that needs to be discharged before I can safely touch things, then I know that I need to ground the negative, which is usually what this stripe represents in an electrolytic capacitor, the negative, although it could be the positive. It depends on the manufacturer. I rarely see those, but don't just assume that the stripe is the negative. But I need to take, and when this is in a circuit, I need to take a lead to ground in the circuit somewhere, and then I need to take a positive, I need to take that lead that goes to ground and take it to the positive terminal and then drain the capacitor. And then it will be safe to touch and safe to move on from there. There are some exceptions to that rule, and we will talk about that, but that's basically what you need to know to be safe around things. Now, here's not the total rest of the story, but here's some other things to consider and ways to increase your chances of success and safety and staying alive. So, first thing, where are you going to find these? What do I need to, I want you to be cautious if you're opening any piece of gear or whatever, but what do you really need to be paying attention to? So what you need to be paying attention to is the larger sized electrolytic capacitors in power supplies, because they're used in power supplies to smooth out the power and to filter the power and to do a few other things. So when you open something up, you should, number one, a good rule around any high voltage or an unknown voltage is don't grab things with both hands, because it makes it a lot easier for the current to pass from arm to arm and through the heart and stuff like that. So when you're working around stuff that's unknown, or even if it's live and there's high voltage, try to keep one hand. There's the old thing about people keeping their hand behind their back, and try to just use one hand. And if you're probing for voltages, use one hand and probe for your voltage, and not give the electricity a chance to go through your body through both hands. Of course, a few other things, particularly if you're working around live high voltage, take off the jewelry, stuff like that. You want to be careful about that. Also want to be careful, I'm not wearing long sleeves, but long sleeves with maybe a button that has metal, basically metal things. You want to be watching out for that. You don't want to be shorting things out unintentionally. And then one other thing about shorting things out, you saw me go and short the leads on this, and then we saw a spark when I did it, and that discharged the capacitor. And that's fine, because again, I know this is low voltage. I know I charged it with a 9 volt. I looked at the meter and it said 9 volt, and I know that this is a maximum 25 volt capacitor, because it's labeled on here. So I know that that was fairly safe to do. But when you're dealing with capacitors in power supplies, in things that plug into the wall and things like that, and when the capacitor is also in a circuit and actually soldered in a circuit board and all that, you don't want to just be shorting out the terminals with, some people, old school people would go and take a screwdriver and just go and short terminals and stuff like that. You don't want to do that, because a great deal of energy can be released. Remember, I was talking about heat, through the body being one of the dangers. Well, it's because a great deal of energy can be released from a capacitor, and that energy, if it's released in a circuit board or in a component that's in a circuit, there's a lot of heat in that one spot. If I'm shorting out these terminals, like this, and there's a spark here in that could be a super hot spark and discharge of electricity. And where this is soldered in, you could melt circuit board traces, or God forbid, you could cause a voltage surge or something that would affect something farther down the circuit or in the circuit, and you could destroy more things. So basically, the idea of in circuit just taking a screwdriver or something and shorting out terminals, not a great idea. What does work is to take and find a ground somewhere, boom, in your circuit. This will be where the negative power supply is, a ground rail. If you don't know what to look for there, then you probably need an additional video besides this one in terms of working around in circuits and stuff. But you ground one end of a wire, and then you come up on the positive end. You notice I keep saying positive end, because if you go, the negative end is going to be at ground, and that's going to be at the same potential, so you're going to show 0 volts there. There's not going to be stored power. So you need to go to the positive end, and then you can drain that to the ground of the circuit. There's also other things that you can use. So I mentioned these power supplies, and some of these power supplies, things can store a lot of power. So I said a few times, this is a 25 volt capacitor. There could be 60 volt, 50 volt, 100 volt, 400 volt. You don't want to be getting shocked by the charge stored in a 400 volt capacitor. It may not be fatal, and that's an important thing. Even though I'm talking about electrical safety and talking about keeping you alive, you can make unfortunate contact with voltage and survive. This isn't instantly fatal. And I talked about 100 volts. That's typically the crossover point between low voltage and high voltage in terms of when you're talking about National Electrical Code and other things like that, and consumer devices and things. Well, it's not magic. At 98 volts, it suddenly doesn't become non-fatal. And at 101 volts, it suddenly becomes fatal or something like that either. It's just a way to classify things. So I've gotten shocked by high voltage before, doing things that I should have known better about, and I didn't die, or I didn't fry a finger and have to have an amputation or anything like that, but it also didn't feel good. So when you discharge, you need to discharge appropriately for the amount of voltage that you are dealing with. So a little capacitor like this, I can use a piece of wire like this. You can use test leads. There are things that are sold in order to discharge capacitors and things. There's something that you can buy or make. Old school people would call a chicken stick. It also would more technically be known as a discharge device. But the point being is that it is a probe. It is a probe or maybe a clip or something that would have wire, but would also come to physically a stick, an insulated piece of wood, a stick, and then would have a contact at the end. And that allows you to be farther away from the high voltage and get the probe into where the voltage is and discharge it. And sometimes these devices, a chicken stick may have some kind of internal resistance or impedance in order to drain that voltage more smoothly without causing sparks at a capacitor or something, and also without generating too much heat and melting down wires or things like that. And where do those things, okay, so there's the ways that you can discharge these things. And where are we going to find these things? So consumer electronics, which could include something even like this meter. But anything that has a power supply is going to have, if you plug it into the wall, somehow it has to take that wall power, 120 volts in the United States AC, and has to convert that to a different voltage usually, and also to DC, and sometimes multiple voltages and things. And there's a variety of ways this can happen. It can be with transformers, it can be with MOSFETs and high frequency switching and pulse width modulation and various types of power supply designs. But the point is that where that part of the circuit is, where the line power comes in and then it gets converted and smoothed and all that kind of stuff, that's where you will find these things, because these are smoothing devices. So that is why they'll end up in that place. So the place to look is in a power supply and near a power supply and near where the power comes in. And the higher the voltage, the bigger these things will be. So I mentioned consumer electronics, and that's where you'd find something like this. And that could be up to, it could be any one of a number of things, but line level things, mixers, small powered speakers, for instance, something that, only is doing 30 watts or 10 watts or something like that, not 100 watts or more, something like that. Okay, so those kind of devices. And then we start getting into more voltage. So particularly if you're a musician and you're dealing with guitar amplifiers or any kind of music amplifier, when there are tubes involved, tubes run anywhere from 200 to 600 volts. And so in the power supplies that power the tubes, you're going to find really large and also high capacity capacitors. And there's a lot of places where really high and lethal voltages can be stored there. So you want to make sure that you are measuring and discharging these things, okay? Another place is in TVs of various types. Now, you have to be of a certain age to remember CRTs, but they are still around. A lot of us, though, remember those. The CRT, the picture tube, the CRT inside of a television is actually a giant capacitor, runs at 20,000 volts. Again, it's not necessarily fatal, but you do not want to accidentally make contact with 20,000 volts. Bad things could happen to you as well as to the rest of the stuff, which is why you will see a CRT has from its transformer that powers the CRT has a really big, thick cable that comes up and a big rubber insulator where it plugs in. And that's why they say danger, high voltage, authorized personnel only kind of thing. You should know what you're doing with that. And you wouldn't use these sorts of things. They make special 20, 30, 40,000 volt probes, discharge devices, and measurement tools, a couple $100. And if you're going to be working with that stuff, absolutely get that. Don't mess around. Getting back to audio, ham radio or classic radio gear, any older radio gear, again, tubes are going to be in there. If you see the things to look for, if you look through a grill and you see glowing bottles of glass, that's tubes. Or if it's really heavy, you may have heavy transformers and things like that that are providing high voltage. So where there's tubes, there's going to be high voltage, and that's what you want to be careful about. Again, with the TVs, we've got the CRT with the picture tube, but even with flat screens and newer stuff like that, they may have to generate high voltages for, say, a fluorescent tube that acts as a backlight. Now, a lot of this, they've moved to LEDs. A lot of these things are much lower power. Again, think about it. If you've got a 65-inch TV that you can lift by yourself, that's probably not got very much high voltage going on in it. It's probably LED backlight. If it requires 3 people to pick up a 65-inch TV and mount it on a wall and you can barely handle the thing, it's probably a plasma or something like that, and it may have fluorescent tubes and things like that for the backlight and be at much higher voltages. So if you're going inside of TVs of any kind, flat screen or CRT or anything, you definitely want to beware of the voltages and cognizant of the fact that there could be high voltage, and looking for things to measure and discharge. So if you take nothing else out of this video, measure and discharge, and that's going to keep your gear working, and it's going to keep you safe and alive. And that's probably it for this video. Like I said, mostly this is shop and inside gear related. I might, especially if there's a big demand, I might do a show site video, which is completely different. I mean, some equipment is the same. We still have the meter, of course, but is a completely different set of parameters of what we're looking at in terms of safety, but a lot of the same rules apply. And just one thing that I will say last, I mentioned this earlier about standing on concrete in a puddle, which is kind of a joke that we use when talking about electrical safety. Just like I've said, don't solder things in shorts. Don't work on electronics, particularly if it's live and plugged in and you're doing things. Don't work on that stuff barefoot. If you do, and you have a bench set up, have a big, thick rubber thing that your feet are on. Don't allow yourself to be easily grounded. You should be grounded. That's another joke. Don't allow yourself to be easily grounded while you're working around high voltage. That's going to save your life and your gear. So, again, if you heard something either that doesn't make sense or you want to expand on or have more discussion, post in the questions. If you heard me say something that you know is completely wrong, and how could you have told people that, then bring it up in the discussion. And I think that's enough for this. So I will wish you safe show and good luck in all of your electrical endeavors, and see you next time.